Hey everyone, welcome back to the channel. And as we know, we have talked about some of the food engineering problems in the previous two sessions. So this is the third session, and we are going to talk about one of the important problems in the food engineering, and it's energy balance. Okay, so without wasting any time, let's directly get into the questions of energy balance. Before that, if you like this content, make sure to leave a like and comment in the comment section if you have any doubts, and subscribe the channel and follow our Telegram channel if you want to know more updates. Okay, so let's get into the content. First of all, energy balance. So to talk about the energy balance, first we need to know the law of thermodynamics, which is the basics, right? So what is the first law of thermodynamics? The first law of thermodynamics is energy can neither be created nor be destroyed, which we have already studied many times in our childhood, right? This word energy can be neither be created nor be destroyed, which means whatever energy is available in the system, it will not be destroyed or created. Okay, so we can convert this word into a formula. For example, total energy entering into a system, because now we are mentioning everything as a system. If you have studied the mass balance previously, or the water activity problems, then I have mentioned everything as a system. It is the easiest way to calculate a certain problems, so we can call that as a system. Okay, so the total energy enter into a system and total energy leaving into a system, if anything changes happen between entering and leaving, and the change is the total energy. Okay, so the total energy entering the system minus total energy leaving the system is a change in the total energy. It's simple, right? The E in minus E out is the delta of system, change in the total energy of the system. Okay, now let's see how to calculate the change in the total energy of the system in a closed system. Okay, which is actually equal to the heat added to the system minus the work done. Okay, so for example, if the energy has to be spent in some way in a closed system, means the energy cannot escape, right? Then the energy has to added in the system, and it has to do some work in the system, because it can be converted, as it mentioned here. It cannot be created or destroyed, but it can be converted into another energy. So that's why the heat is added to the system minus the work done by the heat, let's say, in the system. So delta E is the change in the energy, is depend on the Q, which is the heat, minus the work done. Okay, it's pretty simple. It's actually derived from this formula only. Now what we are going to do is, we are going to debunk every single unit in this specific equation. If you know every single unit in this equation, you can solve the problems. Don't worry about it, I'll debunk it inch by inch. Okay, so first let's take this one, change in the energy. So change in the energy means internal energy, kinetic energy, and potential energy. That's right? So if you calculate all this energy, you will get the change in energy, because obviously it is a calculation of all the three energies which is present in the system. So you have to calculate all the three energies. And you know the formula for the kinetic energy is 1 by 2 mu square. M is the mass and u is the velocity. And here the potential energy formula is mgh. Okay, m is height, h is the height, g is the gravity, and m is the mass. Okay, so the formula for kinetic energy is 1 mu square, 1 by 2 mu square, and potential energy is mgh. Okay, so just remember it. This is not that much important, but you have to remember it. Okay, see, here is a trivia question. See, in the mass transfer, if it is a closed system, the mass cannot go beyond the boundaries, right? That what we have discussed. So if this is the mass, if for example in the canning, if the liquid is there, the mass cannot go out. Whatever the mass present inside, it will stay inside. Whatever it is cutting the system, we have to consider, right? But here in the energy, it can transfer, because it reacts with the surroundings. for example, like heat, cooking and pasteurization, etc. So that's why heat and work is involved in this reaction. Okay, now we have debunked the like change in energy. Now let's talk about Q. Q is a heat, or we can like the unit of the heat is joule, and there can be a positive heat or negative heat. What I mean by that? Simple. Positive heat is something that the heat is transferring from surrounding to system. Means the system is actually gaining the heat. If the system is losing the heat by losing the heat, then it is a negative heat. Okay, so it can divide it into positive and negative. That is the first thing you need to know. Okay, now let's take a look at this formula. Q is the thermal energy which we are going to find out. Q is equal to M, which is mass of the certain product, under the heat capacity and time. And the time is actually changing from T1 to T2. Means throughout the time, the temperature and the heat capacity is actually changing. So the formula is Q is equal to MCT. See, MC and DT. DT is a small time, that's why we are using a DT. Okay, but here is a point. If we are using the constant pressure, if the pressure is involved, then it's actually CP, which means it is a specific heat, it's not a heat capacity. Okay, so the formula will be MCP, and if I use the integration, it is T2 minus T1. So Q is equal to MCP T2 minus T1. This is the formula for the heat capacity. This is the formula for the thermal energy. Okay, done. See, if the volume is involved, then we have to replace the Cp with Cv, and we have to work the formula accordingly. But here is an important point. Here enthalpy is also involved. So that's why using enthalpy, which we represent as H, we can also calculate the Q. Change in the enthalpy, which means H2 minus H1, is also equal to Q, which means del H is equal to Q. Change in enthalpy means we will put del, right? So del H is equal to Q, which is equal to MCP T2 minus T1, which means change in enthalpy is also equal to Q, which is also equal to MCP T2 minus T1. So this is what we come up with the end of the reaction. Done. Now we have done with the Q, which is what? Heat. Now we are moving on to work. Work we represent in W or joule, is the unit of the work. Other than temperature, all the other interaction between the system and surrounding is work. Example, the movement of the piston, which has nothing to do with the difference in temperature, then that is called as work. All the other thing which does not has a temperature difference, that interaction between system and surrounding is work. That's how we have to understand the work. And there is a positive work and negative work. Positive work, when the work is done by the system. For example, if the system moves the engine, like in a piston, then it is a positive work. If the work is done for the system, for example, if you want to heat a certain product, the product is the system, then the work is done for the system. It's not by the system, for the system, which is actually opposite to the heat, right? Which is actually opposite to the heat which you have studied earlier. So here heat gain and heat loss is basically the opposite of what we have studied in the work. So when the work is done by the system, it's positive. When the work is done for the system, it's negative. We can easily understand, right? Now here is a formula. dW is a small work which is done by the pressure, which is force into the small change in the system, which is ds. And why here is minus? Because we don't know whether this is positive or negative. So that's why we have included a minus symbol. When we integrate the same thing, like for example, change in the work from 1 to 2, and here also it's 1 to 2 and FTS, then obviously when we integrate, we will put S1 minus S2, right? So force into S1 minus S2, and S1 minus S2 is the small change in the system, or del S, we can say. Now I am going to consider few of the forces. Okay, I'm going to replace the F. So first I'm going to replace as a moving boundary. If the boundaries is actually moving, means it is not it's a closed system, but it's a moving closed system. It's a moving closed system. If it is a moving closed system, then pressure is involved along with the volume. Okay, so 1, 2, P and dV is involved. And if gravitational force is involved in the force, then mg z2 minus z1. Z and z is the smallest distance. Okay, it's the smallest. Z means distance, small distance. Okay, then if the velocity change is involved, then m divided by 2 u2 minus u1. U is the velocity. Okay, u2 square minus u1 square. If the shaft rotation is involved, it is 2 pi n into delta. And here this torque symbol is mentioned, and here how much of revolution happened because of the shaft is n. So 2 pi n into torque. Okay, then if the frictional force is involved, it's minus frictional, because the frictional force is against the work which we expecting to do. That's why it's minus. Put all that in the work. The W is equal to PdV minus this is kinetic energy, potential energy, and the frictional energy which we have mentioned here. So put all this energy. This is the work done. Now we have seen all the three things, del E, Q and W. We can simply put that in the equation and we can solve it. But we also need to know in the open system also. Now we have only seen the closed system, but what about the open system in the energy? So to study the open system, first of all, let's understand the system. For example, here in the open system, as you can see, it's open. I am putting a product, and that product is going under a pressure in the specific area. And now here in the system, the work is actually done, and that work is actually flow. The liquid is actually flowing. That is also a work done, right? So flow, I am taking that flow as a work done. For example, see, first let's take what is a F here. F is a force. That force means pressure into area. Force that requires to push, right? Push the liquid or push the product which we are going to do the work. Okay, now how the work is done? The work is done in the mass flow. Okay, that means F into L. F is the force, L is the distance traveled by the specific mass, and we can substitute this one. This will come PAL, and while solving we'll get PV. The V is the volume of the system, volume of the liquid. Okay, P into V. Now we have to apply the same thing here. So instead of putting the PdV or something, here we are using PV. So in this energy, there is no friction energy or something here, but the internal energy is there, potential energy is there, kinetic energy is there, and PV is there. PV is the work done. Okay, and I know the formula. It is 1 by 2 mu square, which we have already seen earlier. It is mgz plus PV. I'm just substituting here, okay, just for the sake of understanding. Okay, now I'm considering an other factor, which is now that is over. This is for the open system, that is for the closed system. Now I'm considering another factor, which is called a steady state. Okay, in the steady state, whatever energy you are giving in, you are expecting the energy is to coming out. Means, for example, let's take this example in a very simplest way. If you are giving 10 force of energy, and you are expecting the same 10 force of energy in another format, like 10 degrees Celsius or something like that, or if you are giving 10 degrees Celsius of some energy and you are expecting 10 Newton of force or something, then it is the energy balance. Means it's a steady state. Energy in is equal to energy out, and del system is 0. Why? Because if E in is equal to E out, this del system is 0. Okay, now this steady state, we are going to take that as a base equation. E in is equal to E out, and put all the values we known for E in and E out, then finally we will get this big equation. Okay, you have to remember this equation if any question comes, because you know all this value. The first is u. U2, u means you already know it is velocity, and this is 2. Okay, and g is gravity, z is a small distance, p is the pressure, and this is actually density. This symbol is for the density. Okay, so it's actually repeating, and here two new symbols is there. One is qm and wm. qm means transfer of heat per unit mass, and ws means transfer of work per unit mass. Okay, here the work is done, and here the q is actually transfer of heat. So that's it. This is the ultimate formula which we can get it from the equation. Okay, now let me tell you one more important point which is not mentioned in above equations. See, we are considering that this heat is not involving with the pressure, so I am taking a constant pressure. This constant pressure will affect the phase change. Why I am telling you is simple. Before you understand about the phase change, let's talk about what is a latent heat. Latent heat is something that the heat energy is actually absorbed or released. Okay, so I have a heat energy. That energy is either absorbed by the system or it is released by the system. Absorbed or released by the system. But during this phase, this will lead to a phase change. First of all, this absorbing and releasing the energy leads to phase change. Phase change means solid to liquid to gas, or any of the phases changing in between. For example, like melting, freezing, vaporization, condensation and all. Okay, this is the important point. Without corresponding change in the temperature, which means the heat is actually losing and gaining, but in the system temperature remains constant. For example, the temperature remains same at 30 degrees Celsius only, but the phase is changing from solid to liquid to gas. Okay, you might be wondering how that possible, right? Let me tell you this example. Okay, so let's take this example. So before that, there are two things to understand. Energy is actually changing, but temperature does not change in the latent heat. Okay, so let's understand what is a latent heat. Let's assume that if ice is melting at 0 degrees Celsius, okay, that means here the pressure is constant and temperature is also not changing. But what happened, because of the latent heat present in the ice, it is actually 3.2 kilojoule per kg is there. Because of the latent heat of fusion, this ice is started to melt even though the temperature doesn't change. Same goes to the water into steam reaction. Here at the 100 degrees Celsius, obviously the water will turn into steam. So here the temperature is actually constant, but because of the latent heat present in the steam water, it will convert it into a vapor, and the value for the water is 2257.06. This is the latent heat present in the water. If you check the latent heat, this is the value you will get. At 0 degrees Celsius, you will get the 3.2 kilojoule per kg, and at the 100 degrees Celsius, you will get 2257.06 kilojoule per kg. Okay, now you know what is a latent heat. Latent heat is something, energy is actually affected by absorbed or released, but the phase is changing without changing the temperature. Okay, now you know all the things you need to know for the solving of any energy change questions. Let's solve one or two questions. First, let's solve the question which is asked in the previous year patent exam question. Okay, so here the question is 5 kilogram of ice at minus 10 degrees Celsius is heated to melt into water at 0 degrees Celsius. Actually, we have a ice at minus 10 and we are heating it to 0 degrees Celsius to melt the water. Then what happened? We are not stopping there. We are giving some additional heat and added to vaporize the water into steam. Okay, the saturated vapor exit as 100 degrees Celsius, means we are giving an additional temperature, and it's actually 100 degrees Celsius and it's turned into vapor. Now I need to calculate the enthalpy values. Okay, enthalpy is what? Enthalpy is actually change in enthalpy is Q only. I'm going to calculate Q. Okay, so before that, there is a few values they have given. One is a specific heat of ice is 2.05. Okay, that's good to know. And specific heat of water is 4.12. Say 4.182. This you need to know because this is asked in many examinations also. 4.182 you need to know. And latent heat of fusion, this we already studied previously. And for vaporization, it's actually 2257.06. Okay, all the things we already know previously. Now let's make a drawing. This drawing is not given in the question. That means you have to assume yourself or you have to draw yourself. So what happened is there is 4 phase change. You might be wondering, that is only 2 they have mentioned. Like they have mentioned from -10 to 0, which is the first one. And you might be saying that it for additional heat is mentioned from melting the water here to steam. So 2, only 2 system you are reading in the question. Then why we need a 4-step graph? Actually, latent heat is involved. I'll tell you how. First, what happens is the water is heated from -10 to 0 degrees Celsius. This is the first AB. Okay, where we are actually using, we are actually heating to reach it to the 0 degrees Celsius. Now from B to C, it's actually latent heat, which means the temperature is not changing. But the liquid is actually started melting because of the latent heat of, there is 2 latent heat of fusion. From the C to D, I am again increasing the temperature and again heating. And once it reaches the 100 degrees Celsius, now also it's latent heat of vaporization. It continues to change in the water vapor, but does not change the temperature. Latent heat of vaporization. So now you know all the values and all the given. Okay, so what is given? You need to know it is 5 kilogram of ice. All the things are mentioned here except 5 kilogram of ice. Okay, let's solve the question. So before solving the question, I need to divide this question into 4 zones. Okay, because of the difficulty. So the first zone is actually AB. So the zone is A to B. So I am calculating the enthalpy or temperature difference between A and B. Okay, so del H of A and B, which is equal to Q, which you already know. So what is that formula for Q? Is mCp T2 minus T1. So this is the formula, right? What is M? M is 5. And what is Cp? Cp is actually specific heat of water. But here is not water, it is actually ice. So specific heat of ice is 2.05. So I am putting 2.05 into temperature 2 minus temperature 1. So temperature 2 is actually 0, minus and minus of 10 degrees Celsius. Okay, so it's actually 102.5 kilojoule. Okay, so this is the del H of AB. Okay, done. I have calculated the first enthalpy. Now I am going to calculate the second one, del H of B to C. Here latent heat is involved. See, the formula is actually same, mCp T2 minus T1 only. But here the temperature and the specific heat is not involved. Mass is still the same, 5 only. But because of this, we have latent heat. So I'm going to substitute the latent heat here instead of the Cp T2 minus T1. So what it is actually 333.2. and the answer is actually, if I calculated, 1666 kilojoule. Done. Now the third one, del H C2D. C2D. So this is actually from 0 to 100. It's rising from 0 to 100. So it's actually MCP T2 minus T1, and M is actually 5, and T2 is what? T2 is 100 minus T1 is actually 0, and into CP here I'm going to substitute for water, because in this stage it's actually in the water state. Specific heat of water is 4.182. Okay, into 4.182, so it's come down to 2091 kilojoule. And I have one more phase also, which is H, D and E. Okay, so D and E also same, it's involving with the latent heat. So M into the latent heat, M into the latent heat, H latent. So M is same, 5 only. What is the latent heat for the vaporization? It is 2257.06. So 2257.06. So if I calculated, it will come around 11,285.3 kilojoule. Okay, done. Now I have calculated all the different enthalpies. Now if I add all this one, I'll get the total enthalpy, which is asked in the question. They have asked calculate the different enthalpy values involved, and if they have only asked the different enthalpy values, so this itself is enough. But to make sure that you need to calculate the whole enthalpy, I'm going to put del H, and del H of AB plus del H of BC plus del H of CD plus del H of D, right? So it is actually, if you calculate all the values which is mentioned here, you will get 15,144.8 kilojoule. That is the total enthalpy, or change in the enthalpy, we can say. That's it. I'm done with the question. So this is the question. This is actually pretty simple, and it is asked in the previous year examination. Now you are done with actually both the questions which is asked in the examination. See, this is a quick shout out I want to tell to the students of the patent examination. See, basically the problems which you are going to face is come from the book of this Arpal Singh. Okay, and obviously they are not going to ask some pretty tough questions, like the questions which you are going to face is from the either chapter 1 or 2 or 3 basically. Okay, which is my assumption. So if you want to study more, you can study. I am not telling you that the questions will only come here, but my assumption is whatever the questions which is asked previously, compare that question, then you'll get to know the similar question from that area might come. So all the questions which I have selected as an additional question is actually, it's going to help you that question itself might come into the examination. Or I can say all the question which I'm going to discuss in this series of food engineering problems, any one of the question which I have discussed will definitely come. But I'm not sure about the other question where they are going to take it. But I can surely say one of the question which I have discussed itself will come. Okay, so that's why this is really important to study the similarity of the questions which is asked in the previous year exams and questions. So let's solve one more question in this specific heat. So this is a question. So they have used a tubular water blancher, okay, to process the lima beans, and the mass flow rate is 860. So mass flow rate is actually 860, and it found that the theoretical energy consumed for the blanching process is 1.19. Means at the end of the blanching process, the product is value is 1.17. Okay, the energy coming with the product, and the energy lost is 0.24. So energy lost is 0.24, and the total energy input to the blancher, which means the total energy we are giving is 2.71. Now you have certain values. You need to know how calculate the energy required to reheat the water, which means the water is also living with some energy. Okay, you don't know the energy, so let's call that energy as x. And in order to use this water here, okay, in order to use this water in the energy input, you need to reheat the water. Why? Because this energy which is lost in which is actually lost here and gives some energy here. So whatever the water which is coming out of it, it is going to be less the energy which is given. So you need to reheat some value to make up to this energy. So the first the very first thing which you are going to do is to find out the energy of the living water. Okay, is to find out the energy of the living water. It's actually easiest question out of all, but I'm specifically thinking that this question is going to come. I want you to do only one thing. If this question actually come in the examination, please, if you have watched this video and if this question actually come into the examination, please come back to this video and like the video and mention that this question came into the examination. That is the only thing I want from you guys. Okay, for like making this video, I need nothing else. I'm not charging anything. I'm doing it for free. I'm doing it for fun. But the only thing I'm expecting from you is the recognition which you guys are giving. Okay, so this is a simple thing which I'm asking from you only if it is asked in the examination. Okay, so let's move on to the question. So in this question, first I need to calculate the energy which is leaving. So the first thing is the very first thing which we have studied is energy which we are inputting, which is equal to the energy of output, right? So this we have already studied. So let's use this. 2.71 is the energy input, is equal to what are the outputs? 0.24, which is the waste energy losses, plus the product leaving energy is 1.19, plus the x we don't know, energy of living water. So x is equal to, if you solve all this, you will get 1.28. so this is the energy which is coming out of water. But if you want to recycle this specific energy, you need to add some extra energy into it. How much of extra energy you need to add? You need to add this energy, this x, with some y to get the 2.71. Okay, so from 1.28 to you need to add some y to get to the 2.71. So if you calculate the y, it will come around 1.43. So joule per hour. So this is the additional energy you need to add. So the first point is done. Calculate the energy required to reheat the water. Second question is determine the percentage of energy. You already know all the energy, just convert it into percentage. See how you can convert it into percentage. We know if you are scoring, let's say 50 mark in the examination and the total mark for the exam is 100, then how you will solve it? You will solve by 50 divided by 100 into 100, right? So same, do that for all the different inputs. I'll start from here. 2.71 divided by 2.71 into 100, which means energy input is 100%, and energy loss 0.24 divided by 2.71 into 100, which will come around 8.86% of loss, and the energy leaving with the product is 1.19 divided by 2.71 into 100, which will come around 43.9%, and the energy leaving with water, it's actually 1.28 divided by 2.71 into 100, which will come around 47.23. So these are all the other percentage of energy associated with each tree. That's it. I've done with this problem. There is one more extra problem which I'm going to give you. You can take a screenshot of this specific question and you can solve the question and you can give me the answer in the comment section. If you are actually preparing for this examination or preparing for any other examination which is related to the food engineering syllabus, then please make sure to answer this question. I will let you know whoever is answering perfectly in this video. I will give a shout out to that person in the next video, and I can also get to know that you are serious in this preparation of pattern examination, so that I can give you even more videos. Okay, so this is a question and make sure to give me the answer. See, uh, here the degree is not might not be like visible to you, but here degree is there. Okay, 0 degree. Okay, so yeah, that's it. This is a question, so please make sure to give me a answer. That's it. Let's meet you in the next video. Bye.